This video will cover homework questions from section 4.2. In section 4.2, we are asked about the maximum and minimum values of functions. Specifically, we're asked about local maxes and local mins and absolute maxes and absolute mins. So I will go through several problems that follow the typical steps we would need to master to solve problems of this type. So if we start with problems at the beginning of the homework, we're looking at this from a graphical standpoint. And what that means, that stresses the definitions. Remember, we know that there are four definitions. We have four unique, four independent definitions. We have the definition of the absolute max, absolute min, local max, and local min. And these definitions are independent. It's important that we realize that just because we've satisfied one of the definitions has no bearing on whether or not we've satisfied one of the other three definitions. The definitions are all unique and they must all be individually analyzed. So in the beginning, they give us conditions and they ask us to draw a graph. Now, there are not unique solutions to these problems. So the first problem I'll take a look at is problem number 9. And it says we want an absolute max at 5. We want an absolute min at 2. We want a local max at 3. And we want a local min at 2 and 4. So we need to draw a graph. I'll construct my function over here in quadrants 1 and 4. That doesn't have to be the case. At 5, we need a local max. So the tallest our graph can get is 5. So if we just put some hash marks down here and we pick a spot, and we say, okay, I'm going to let this be my local max. It's going to happen right here. And then we continue. We're like, well, our absolute min is going to be at 2, right? 2's here. So we'll make our absolute min right here at 2. Now, if we just stop right here and we draw a graph, right? Say perhaps this was all they asked us to find, and we construct a graph. And our graph goes like this, for example. Well, this would be wrong because that's not a local min, right? This graph implies it's going to continue. I'm sorry, that's not an absolute min. This implies it's going to continue down. This is going below that. So we're going to have to change this, right? We're going to have to change this. And we're going to say, okay, that's going to be the absolute min. So maybe our graph comes up and then it becomes horizontal. It has a horizontal asymptoted 3. And maybe on this side, it does the same thing. And it has a horizontal asymptoted 3. And now we've satisfied their conditions. We have an absolute max at 5. That's the tallest our graph is going to be. It's our largest y value. We have an absolute min at 2. That's the smallest y value our graph is going to attain. So we would be okay. But if we continue, right, if we say we've done this and we think we're on our way to solving problem 9, problem 9 says we have a local max at 3. Okay, well, a local max at 3. 3's here. We could construct the graph to have a local max at 3. But what I want you to pay attention to is this is also a local max. right? That's a local max. And they didn't tell us that we wanted a local max at 5. They said 5 was going to be an absolute max, but it's not a local max. So this is what I mean when I say these problems deal with definitions. They want us to make sure we understand the definition. How do I make something an absolute max and guarantee it's not a local max? Because the local max is not at 5. Well, endpoints cannot be local maxes. That's what we said, because there's no open interval around that point. So I'm going to start my graph here, and I'm going to put a dot there, and that's going to be the beginning of my graph. And now my graph is going to begin there. The rest of my graph must be lower than 5 because that's going to be my absolute max. Now my absolute min is going to be at 2, but it's also a local min. So if I wanted to, I could have my graph come down, go through this point. Now that is the lowest point on my graph. And more importantly, not only is it an absolute min, it's a local min because it's the smallest y value in a neighborhood about this x value. And that's the definition of a local min. So we've satisfied our absolute max at 5. We've satisfied our absolute min at 2. We've actually satisfied our local min at 2. Now we need a local max at 3. 3 is here, right? 3 is here. So over here we'll make a local max. So my graph's going to continue up. Now it's going to continue down. That's a local max because that's the largest y value in an interval, open interval, about that x value. But I also need a local min at 4, right? A local min at 4. So how am I going to get myself a local min at 4? Well, 4 is here. So this is a local max. My graph has to continue down. So now my graph could reverse itself, come up. I need it to be a local min. So my graph could come up, turn, can't get above 5, right? Can't get above 5. And go back down. And now I need this to be a local min. So I'll make my graph have a horizontal asymptote here at 4.5. And now our graph has a local min at 4. So they want us to learn our definitions, right? That's what these graphical problems are about. Now, after we get done with these graphical questions, they give us another type of question. These are more mechanical, all right? They involve a lot more calculation, and they involve some definite steps. For those of us who like steps, we can employ steps to do these kinds of problems. If we look down at problems like 25, for example, or 29 or 28, we'll start with problem 25. Problem 25, they give us a function f of x equals x cubed plus 3x squared minus 24x. And the instructions say find the critical numbers. Now, we need to recall a critical number this is an x value where f prime of x equals 0 or f prime of x fails to exist. That's our definition of a critical number. So to find a critical number, we need the derivative. We're looking to see when the derivative is 0 or the derivative fails to exist. So if we take the derivative of this function, we get 3x squared plus 6x minus 24. And now we can factor that, right? Because we're going to want to set it equal to 0. This is a quadratic. When we want to set a quadratic equal to 0, we always factor. So let's just go ahead and do that right now. We can take out a 3. That leaves us x squared minus 2x minus 8. And we can factor that even further. That's going to be 3 times. And this is going to be x minus 4 times x plus 2. All right. Now, what are we going to do with our derivative? Well, we're going to look for critical numbers. So to look for critical numbers, we're going to do 2 steps. First, we're going to take our derivative. We're going to set it equal to 0. So we're going to tell our instructor, this is where I'm doing that work. We're going to head it. We'll put a heading up here. F prime of x equals 0. So I'm going to take 3 times x minus 4 times x plus 2, and I'm going to set that equal to 0. Now, we know from algebra that if you have a product that equals 0, one of the factors must indeed be 0. That's the only way we can get a product of 0. That's called the zero product property. And we said that back in algebra. We said if a times b equals 0, then a equals 0 or b equals 0. That's our zero product property. So if we take a look at this, we know 3 is never going to be 0. It's a factor, but it's not going to be 0. So from here, we get the fact that x minus 4 could be 0, or x plus 2 could be 0. If we solve this, we get x equals 4, or we get x equals negative 2. So those are critical numbers. Those are our critical numbers. Okay. Now, where are we going to go from there? Well, it said find the critical numbers of the function. We found 2 of them, but the definition of a critical number includes the condition that the derivative might fail to exist. So we have more work to do. Over here, we're going to take the derivative, and we're going to check to see where it fails to exist. When we look at our derivative is a polynomial, 3x squared plus 6x minus 24. That's a poly. F prime of x is a poly. Thus, f prime of x exists everywhere. All right. There are no places where the derivative fails to exist. Polynomials exist everywhere. So our 2 critical numbers for problem 25 are x equals 4 and x equals 2. Now, these are the steps we're going to use every time we look for critical numbers. Let's do another one. That was number 25. So if we look at problem 29, okay, and we'll take a look at problem 29. Let's erase this here. I'll leave these definitions up here just in case we need them again. Let's take a look at problem 29. Problem 29 gives us a quotient, right? 29 says g of y is equal to y minus 1 divided by y squared minus y plus 1. Now, we know that when we are asked to find a critical number, our first step is going to be to find the derivative. So the first thing we'll do is do the quotient rule here. We'll get g prime of y equals. Now, we're going to get y squared minus y plus 1 squared here, right? We square the denominator. We put the denominator here. We multiply by the derivative of the numerator. The derivative of y minus 1 is 1. The derivative of y is 1. Derivative of a constant is 0. Minus. We write the numerator here. We multiply by the derivative of the denominator. That's going to be 2y minus 1. And now we have some algebra. Right? We don't expand the denominator, so that's going to be y squared minus y plus 1 squared. We're going to multiply here, but when we distribute the 1, all we get there is y squared minus y plus 1. Here we have minus. Don't forget your grouping symbol because it's minus this product. That's going to be 2y squared. Negative 1 times 2y is minus 2y. -1 times y is minus 3y. And then -1 times -1 is going to be +1. So when we simplify the numerator, we get y squared minus 2y squared. That's going to be -y squared. We get -y squared plus 3y. So that's going to be plus 2y. And we get 1 minus 1. Sorry, 1 minus 1. That's going to be 0. And our denominator is going to be y squared minus y plus 1 squared. Now, again, we're going to factor this as much as possible. We're going to take out a negative y here. So if we take out a negative y, we get y minus 2. And on the bottom, we have y squared minus y plus 1, quantity squared. Once again, we're going to go through the steps. We were asked to find the critical numbers. There are 2 steps to that. The first step is we're going to figure out when does the derivative equal 0. Now, our derivative is a fraction, right? We know from algebra that fractions equal 0 when the numerator is equal to 0. So we're going to take our numerator and we're going to set it equal to 0. Minus y times y minus 2 equals 0. Again, we're going to employ our 0 product property. So we're going to get these 2 factors, minus y equals 0 or y minus 2 equals 0. Solving this, we get y equals 0. Solving this, we get y equals 2. But remember, there are 2 steps for looking for critical numbers, not just where does the derivative equal 0, where does the derivative fail to exist? So we're going to then do our work and we're going to see where this fails to exist. Now we do have a quotient here. Remember, quotients fail to exist when the denominator equals 0. So we're worried about y squared minus y plus 1 equals 0. We don't really care about the square because if we put the square in here, we take the square root of both sides. Square root of 0 is 0, and we're back to this. Now, does this equal 0? Ever, right? That's what we're really worried about. Is this possible? Well, it's a quadratic. It's going to equal 0 if it factors, but we can try to factor that. We can't factor that in our head, but we can use the discriminant to see if it actually has solutions over the reals. Remember, the discriminant is b squared minus 4ac. So in this case, we get -1 squared minus 4 times a, which is 1, times c, which is 1, and that gives us 1, -1 squared, minus 4, that's less than 0, so no real roots. Because there's no real roots to this quadratic, that means the denominator never equals 0, which means that the derivative never fails to exist. So these are our only 2 critical numbers. It's almost like we took all those algebra classes for a reason, huh? All right, we'll look at one more of this type of problem. So that was number 29. That involved a quotient. The first one involved a polynomial. Let's go ahead and jump down here and take a look at number 35. It involves trig functions, right? So 35 says f of theta equals and we get 2 cosine theta plus sine squared theta. Now, we can jump right in and we can take the derivative because we're looking for critical numbers, and to do that, we need the derivative. If we do take the derivative, what do we get, right? What do we get here? Well, if we take the derivative of cosine is negative sine, so that's minus 2 sine theta plus. Here we're going to have to use the chain rule. Down is going to come the 2. The derivative, right? The derivative, this is squared, right? This is really sine theta squared. So down comes the exponent. We have sine theta to the first power now, because we take away 1, and we multiply by the derivative of what's inside. Sine's inside, the derivative sine is cosine. So this is our derivative, negative 2 sine theta plus 2 sine theta cosine theta. Once again, we're going to factor. We'll take out a negative 2 sine theta. Negative 2 sine theta divided by negative 2 sine theta leaves us 1. When we take the negative 2 out of here, we get minus. We're taking out the 2 sine theta, so that leaves us cosine theta. So every problem follows the same steps, right? The same process. We take our function, we take its derivative, and we know where to go from here. We're going to set it equal to 0. Now, when will this equal 0? Well, once again, it's a product. It's negative 2 times sine times 1 minus cosine. So where do we go from here? Well, we take this. And we set it equal to 0. We're going to employ the zero product property again. Negative 2 is not 0, so that factor we can ignore. So that's going to give us sine of theta equals 0, or 1 minus cosine of theta equals 0. So we have to answer, when does the sine of theta equal 0? Now, a quick sketch of our friend sine. Will allow us to see that that's 0, that's pi, that's 2 pi, that's negative pi, that's negative 2 pi. So sine equals 0 at integer multiples of pi, because this is going to be 3 pi and 4 pi. So we're going to write this. We can't make that list, right? We can't write all those down. We could try to write a set that looks something like this. Well, 0 plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, comma, dot, dot, dot. We could do something like that. That's not really an elegant solution, but it expresses what we want to say. A better way to say this would be that we're going to get k pi, where x equals, of course, k is an integer. Right? That's a better solution to this type of, or a better way of expressing this type of set. Now, we also have to worry about, right? I'm going to move this over because that went a little long. 1 minus cosine theta equals 0. We have to solve this. We can move the 1 to the other side, the cosine to the other side, and we get cosine theta equals 1. Again, we can take a look at a graph of cosine, right? Our graph of cosine goes like this. And we can ask ourselves, when is this going to be 1, right? When is it going to be 1? Well, it's 1 here, here, here. We know that's 0. We know that's 2 pi. We know that's 4 pi. We know this is also negative 2 pi. So we need 0, 2 pi, 4 pi. Again, we could write that as 0 plus or minus 2 pi, comma, plus or minus 4 pi, comma, dot, dot, dot. But an easier way to write that, a better way to write that is, I'm sorry, I made that an X. That should be a theta, huh? Theta equals, we want the even multiples. To get the even multiples, we take 2, and maybe we use n this time, 2 times n pi, where n is an element of the integers. Because if I take an integer and multiply by 2, I get an even integer. Now, to be perfectly accurate with our result here, 2 pi, 4 pi, 0, 2 pi, 4 pi, 0, negative 2 pi, negative 4 pi. Those are actually over here as well. So we don't technically need to write this answer because these solutions are contained within this answer. So when you look in the back of the book, because they are intersection, right, these are contained in there, what you're going to see in the back of the book is something that looks like this. And again, that's going to happen because these answers are inside that set over there. They're already members of that set. So we've already accounted for those solutions. All right, so that's how we find critical numbers of functions. All right, our next big idea in this section was to use what we call the closed interval method. The closed interval method to find absolute mins and absolute maxes of functions on closed intervals. And so if we look at one of the problems they asked us to do here, like problem 43, okay, that's the very first one they asked us to do. It's a polynomial. And again, this is going to work similar to our critical values or critical numbers questions. They're going to start with a polynomial, and that functions get a little more interesting as we move down. So 43, right? 43, they're going to give us a function, and it's going to be f of x equals 2x cubed minus 3x squared minus 12x plus 1. And they give us a closed interval, and our closed interval is from -2 to 3. And again, the instructions say find the absolute max and absolute min on this interval. Well, to make this work, we're going to need the extreme value theorem. Now, in short, the extreme value theorem says if f is continuous on a closed interval a, b, then f attains an absolute max and an absolute min on this interval. We call it the extreme value theorem because it says the function is going to have an extreme value. The key here is we've got to be continuous, and it has to be continuous on the closed interval. We do have a polynomial. Polynomials are continuous everywhere, and we have a closed interval. So this problem is going to have an absolute max and an absolute min. Again, there are a set number of steps or a set of steps that we can use to solve problems of this type. Step 1, we're going to take the derivative. That gives me 6x squared minus 6x minus 12. I'm again going to factor that. That's going to give me 6 times x squared minus x minus 2. And that's going to factor as 6 times x minus 2 times x minus 1. Now, where are we going to go from here? Well, from here, the problem is going to look very similar to the problems we've previously done. We're going to go find the critical numbers. Okay, we're going to find the critical numbers. So that we're going to find the derivative, and then we're going to find the critical numbers. F prime of x equals 0. Just like on the previous problems, we take 6 times x minus 2 times x. Can't believe I made that a minus. It's supposed to be a plus. We'll write that in orange to show we got that wrong. X plus 1 equals 0. We're going to use our zero product property again. See the similarities here? And we're going to get x minus 2. 6 can't be 0. X minus 2 is 0. Or x plus 1 is 0. That gives me x equals 2 or x equals -1. That's 2 of my critical numbers. Now I'm also going to go through the work of checking to see where the derivative fails to exist. Even though I realize that the derivative is a polynomial, therefore it never fails to exist, I'm still going to present this part of my solution. Because if I don't present this part of my solution, then that's going to afford my instructor the opportunity to think that I forgot it. So I want to make sure they realize I know I'm supposed to do this, but it does not apply, right? F prime of x is a poly. So I'm just going to state that so they know it's a poly, therefore it never fails to exist. So I have 2 critical numbers. My critical numbers are x equals 2 and x equals -1. Now we know from a theorem in our reading that if we have a local min or a local max, they're going to occur at a critical number, right? That's one of our theorems. So if we have a local min or local max, it's going to occur at a critical number. We only have 2 of those. Now, we don't know if those are local mins or local maxes. So now we get to the third step. Step 1, take the derivative. Step 2, find the critical numbers. Step 3, evaluate. So we're going to find f of 2. We're going to find f of -1. We want to know which one's bigger than the other, which one's smaller than the other, which one's the min, which one's the max. The extreme value theorem says f attains. We're going to get one. But we also have to remember to check the endpoints, because we've seen in our graphical approach, sometimes your absolute min or your absolute max occurs at an endpoint. Back in the previous problems, we noticed that. So we're also going to check f of -2, and we're going to check f of 3. So now we have to do arithmetic, right? We're going to put 2 in here. Now, remember to put it in the function. 2 cubed is 8, right? 8 times 2, 16. So that's going to be 16. Here we get 2 squared. That's 4. 4 times -3 is -12. Here we get 2 times -12. That's -24, and we get +1, right? So we have -36 plus 16. That's -20 plus 1. This is going to be -19. Now, I don't know if that's an absolute min or an absolute max, because I haven't evaluated the other value. So I put -1 here. -1 cubed is -1 times 2. That's -2. -1 squared, it's going to be 1 times -3 is -3. -1 times -12 is going to be +12, and I get +1. That's 13. Take away 3. That's 10. Take away 2, that's +8. But don't forget to check your endpoints. -2 cubed is -8 times 2. That's going to be -16. -2 squared is going to be +4 times -3. That's going to be -12. -2 times -12 is going to be +24 plus 1. -16 and -12 is -28. Plus 24 is -4. Plus 1 is -3. Now we have to plug in 3. 3 cubed is 27. 27 times 2 is 54. 3 squared is 9. 9 times 3, -27. 3 times 12 is 3 times -12, -36, plus 1. 54 take away 27 is 54 and 27. 27 is half of 54, so 54 take away 27 is going to be 27. Plus 1, 28. Take away 36 is going to be -8. So -19, that's the smallest value, so that's our absolute min. 8 is our largest value, so that's our absolute max. Always remember to plug them into the function, okay? So that's how we go about doing problems with the closed interval method. The rest of the problems are very similar to these. You just take the derivative, go through the same steps of finding the critical numbers. Once you've found the critical numbers, then you proceed to check those values along with the endpoints in